To the 9.7, the forced response of RLC circuit. In the case of the second order, the circuit is like the first order circuit. The solution of that is consists of two terms. X complete T is the sum of natural response plus the forced response. Now, before the previous chapter, we discussed about the natural response of second order differential equation. And now we will discuss about the forced response of RLC circuit. As we discussed in the second order differential equation solution in the engineering mathematics, the form of the forced response is the same with the input response. So generally, you define the form of second order differential equation is x in the second 2 times derivative and first derivative, then term is there. We call that is the first input. Then if the xf is a solution of that equation, then if we insert this xt here and here, then this equation should be satisfied. And to do that, xf t is the same form of this input ft. So generally, when ft is a constant, then the result of forced response will be kind of a constant. If this is the kt, the value here, then the response of the at plus the b. If there is a kt square, then the result will at square plus bt plus c in this way here. If the first function is sinusoidal like that, then the forced response form also sinusoidal. So there is a more general form of the sinusoidal will be a sine omega t plus the pi, or it can be expressed of two variables, a phi or ab is the same case. Generally, we use this form. And if the first function is kind of exponential values, then the response, the first response form also the exponential form. So it's very simple, and you don't need to hesitate to use these the things. This is example over here. I will give you some example. This is an example of this problem. So example 9.71, to find the forced response is IF. So this is a circuit with the RLC parallel circuit, and insert the source like that. Then at first, the source is defined in this way here, the kind of exponential function. And what should we do? We have to make a equation to represent the characteristic of this equation. So at first, we will use the KCL here. So the minus IST plus, we define that is a voltage V. So this current is okay, it's long, but this is plus, because going up here, so plus is, and this current is go out from here, minus V over R, and current is current I, and this current is C dt dV equal 0. Therefore, is the same with V over R plus I plus C dt dV. And we need one equation. What's that? From the inductance, we know that V will be L dt di. So what I wanted to do is the current. So we replace V with the current. So substitute this equation. The is will be 1 over R, and instead of V, we place L dt di plus I plus C dt d L dt di. So is will be L over R dt di plus I plus LC dt square d square I. So we make more simply d square I plus 1 over RC dt di plus 1 over LC I will be 1 over LC is. So to find out IF is a general form of, because is an exponential form, so we can use a exponential, but when you apply it the same form, you can adapt their variables. So we use minus 2t here. So we apply that first there. So we got it. dt square a exponential minus 2t plus 1 over RC dt d a exponential minus 2t plus 1 over LC a exponential minus 2t will be 1 over LC is here. So the result is 4a exponential minus 2t plus that value is 7. Then is 7. 1 over LC is 6. And is is that values. So that is 6. A exponential minus 2t will be 48 exponential minus 2t. So there is a minus 14 a exponential minus 2t plus 6 a exponential minus 2t will be same with 84 exponential minus 2t. So that will be 4 minus 14 and 6. So minus 4 a exponential minus 2t will be 48 exponential minus 2t. Therefore, a will be minus 12. Therefore, IFT will be minus 12 exponential minus 2t ampere. This is a force response, so this is again, it's very simple. But if another problem, example 9 to 7 and 2, if is source input is I 0, that means constant. Then what happened? I have t. The same things. What's that? We can use it. We can use this equation here, and we know that that value is 7 and that value is 6, so this is a 6. So equation is dt squared d squared I plus 7 dtd I plus 6. I will be 6 is. And I is a constant, so there will be 6 I0. So when source is constant, then IF will be constant, like A. Then apply this form over here. Then 0, the 6 A will be 6 I0. Therefore, A will be A0. Therefore, I of t is I0 ut. So this is the same, and this is not difficult. It's a very common thing. So when you do that in the first order circuit, and when you solved the differential equation, when you learn the engineering mathematics, I will cover one more the specific cases. That is this case. Here we have the same example, but the IS is a little different. Okay, we'll do this more time. Look up here. There's something different. This is example. When R is 6 and L is 7 and capacitance is 1/42, then we know that differential equation of this you already studied it so many times. D square I t plus 1 of RC dtd it plus 1 of RC it is is. So we apply these parameters here and here and here. Then d square it plus 7 dtd it plus 6 it will be 1 of LC. I'm sorry, 6 is. So the final target, our final target is we got the complete solution in IT. The same with INT plus IFT. Then here, the IS is an exponential term over here like that. Therefore, we have to let IFT is the same from A exponential, because it's minus 60, so we have to choose minus 60 exponential variables as a form of forced disperse. Well, unfortunately, when you get INT, to get an INT, we can make a characteristic equation here. This S squared I plus 7SI plus 6I is 0. So So s squared plus 7s plus 6 is 0. Therefore, s squared 7s plus 6 equal to 0. Therefore, s1 is minus 1. S2 is minus 6. What's the meaning of here? We call the xn, the natural response t, which is a function of a1 exponential minus t plus a2 exponential minus 6t. So that is a problem. The form of natural response, one of natural response, exponential minus 6t, same with the forced response. So there's a problem. So if you insert this form here, we insert the form here, there, then what happened? dt squared, a exponential minus 60 plus 7 dtd a exponential minus 60 plus 6 a exponential minus 60 will be 6 a exponential minus 60. Then 36 a exponential minus 60 plus minus 42 a exponential minus 60 plus 6 a exponential minus 60 is 0. Then 6 a exponential minus 60 is weird. So to that, a should be 0. So in this case, when the characteristic of equation, the solution of S, the same is the form of the forced response, then when you apply the forced response form to the equation, then the solution is weird. That is because IN has a exponential minus 60 and IF has a exponential minus 60, the same form. Then in this case, what should we do? In this case, we have to, when natural response has same form of input, then first response should have a exponential minus 60 a t exponential minus 60. We should not use that form. We should use this form. So in this case, we applied here this equation here. Then dt squared d squared at exponential minus 60 plus 7 dtd at exponential minus 60 plus 6 at exponential minus 60 equal to 6 it will be 6, right? Am I right? This is 6. IS is a 3, so 6 and 3. 6 and 3 exponential minus 60 in the case here. So that will be solved. Oh, I'm sorry, this is long. This is not 8. This is anyway, this is 3. So 18 here. It was 18. So that result was more complicated, but I will try that. Then at first, with derivative of the here, dtd a exponential minus 60 and plus, not plus, minus 6 at exponential minus 60 plus 7 a exponential minus 60 and minus 6 at exponential minus 60 plus 6 a exponential minus t 60 equal to 18 exponential minus 60 here. Then we do that. The first minus 6a exponential minus 60, and this gets more complicated, but I will try that. Minus 6a exponential minus 60 and plus 36a t exponential minus 60 and plus 7a exponential minus 60 minus 42a t exponential minus 60 and plus 6a t exponential minus 60, it will be 18 exponential minus 60. So first we'll check a exponential 60, a exponential 60, a exponential 60. That's it. So we sum right here, minus 6, minus 6, and minus 6, and plus 7, a exponential minus 60, and minus 36, at exponential minus 60, minus 42, at exponential minus 60, plus 6, at exponential minus 60 will be 18 exponential minus 60. Here we have some mistake here. Actually, because we delivered it with term, because we minus here, so that is not plus, this is a minus. So that is a plus. So plus 36 minus 42 plus 6, so that is 0. So the main thing is minus 5a exponential minus 60 is 80 exponential minus 60. Therefore, a is minus 80 over the 5. So therefore, the IFT here is minus 18 over 5t exponential minus 60. So this way, when we have a same form of that and the first response and the natural response, then we need to modify the first response form is not a exponential but at exponential values. So until now, we get the solution of complex xt is xnt plus xft. We learn how to get the xnt and also how to get the xft in the second order differential equation based on the second order the circuit in case of RLC circuit. So in chapter 9.8 we've get a complete response of RLC circuit in the point of view. To obtain the complete response of second order circuit, I summarize some steps to get it. The first, we was to find out the initial condition. Initial condition is a capacitor voltage or the inductor current, or you can make a initial condition of V0 or in the TD V0. Or you can make I0 and the TD I0. Or you get it V0 and I0. So anyway, we have to get the V0 or and the first derivative of V0. Even though you get two variables, then you can transfer the one of them is to the like that or like that. Anyway, we need to get the initial condition. So if you needed to modify the circuit, then you should do that. The reason to modify the circuit or simplify the circuit is to gather the initial condition. The next, we need to simplify the circuit. Then we can drive the very simple, the second order differential equation. If you remain the circuit is complicated, then it's very difficult to find out the second order differential equation to represent the characteristic of the circuit. So at first, you try to simplify the circuit as much as possible. Then you drive the second order differential equation from the simplified circuit. Then you can find the natural response. Then you can find the forced response. Then in the case of natural response, we remain the unknown variables. Then finally, you make the complete solution xt. Then you fill out to find out the unknown variables using the initial condition. Then you can gather the final solution. This step is exactly the same with the first order the circuit, but only different thing is how to get the x and t. That's the only different things. Okay, this example of series RLC circuit is very simple. So we'll try solve the problems at first here. Okay, I capture of the parameters here. And the circuit is very simple. There are Vs and R and L and capacitor here. So this is C and L and R. We define this is a voltage V and this is current is I. Then our final target is to find the VT here. So I will do these first. What should we do first? Step one is find the initial condition. In this case, we are very lucky. Why? The problem gives us a condition, values. Then their values. We don't need to do that anymore. Then second is simplify in the circuit. In this case, we don't need to do anything because the circuit very simplified, very simple RLC series in the circuit. And third, what is third? Third, drive. Second, other differential equation. We are very familiar with about that because, okay, then I will try to the KVL at first. What's that? Vs is Ri plus L dTd I plus V. And we need one more equation. We use that characteristic over here. What is that? V is same with C. I'm sorry, it's long. I is C dt dV. Because we want to know the Vt, so we eliminate the I. So we substitute I with that equation here. So we got it. The Vs will be R C dt dV plus L dTd C dt dV plus V. Then we can simplify the equation is Vs is Rc dt dv plus Rc dt squared d squared v plus v. So dt squared d squared v plus all over L dt dv plus 1 over Lc v is 1 over Lc the Vs. So then we apply the parameters because R is a 6, L is a 7, C is 1 over 42. So apply here. R is, I'm sorry, I will modify the variables. Okay, this R is not 6, it's 5, and L is not 7, this is 1, it's my law, and capacity is not 1 over 42, it's 1 over 6. I'm sorry, I modify the variable like that. Then we replace, that is R is 5, then L is 1, and LC is the variables. Then we can rewrite, that is dt squared d squared v plus 5 dt dv plus 6v will be 6 vs. That is we got the second differential equation about the v. So vs is their values, so we can remove and we can replace. That is 4 exponential minus 5t. Then the problem is change it, how to solve that equation here. So based on here, we have to find out the first thing is find natural response. That will be characteristic over here. So that from the here we got it. S squared 5 plus 5s plus 6 is 0. Therefore, S1 will be minus 2, S2 will be minus 3. Then V and T can be written here A1 exponential minus 2t plus A2 exponential minus 3t. Then 5, find the forcible response. And why the forcible response? Because the source is a form of exponential, then we can find V of t is a kind of b exponential oh, I'm sorry, this is not 5, this is just t. So because this is the form of the minus t, so we can make a force as form as b exponential minus t like that. So what should we do to get the b? We apply that formula to here. So dt squared d squared b exponential minus t plus 5 dtd b exponential minus t plus 6 b exponential minus t will be 4 exponential minus t. To get it, there's the b, there will be b exponential minus t and plus minus 5 b exponential minus t and plus 6 b exponential minus t will be 4 exponential minus t. Therefore, b minus 5 plus 6, so 2b is 4. Therefore, b is equal to v of t is 2 exponential minus t. So the last thing is 6. is complete solution. There was xnt is this form here. a1 exponential minus 2t plus a2 exponential minus 3t plus, that's it, final first response, plus 2 exponential minus t. Then together a1 and a2, we got it. They use the initial condition of here. First is v0 is a1 plus a2 plus 2 should be the 10. And second thing is the dv is minus 2 a1 exponential minus 2t minus 3 a2 exponential minus 3t minus 2 exponential minus t. Then t is 0, t is 0, that value is minus 2a1 minus 3 a2 and minus 2. That value will be minus 2. Therefore, a1 plus a2 is 8 from here, and minus 2 a1 minus 3 a2 is 0. So from here, a1 is 24, a2 is minus 16. Therefore, vt is 24 exponential minus 2t minus 16 exponential minus 3t plus 2 exponential minus t volt. That is a complete solution of this. It will be complicated, but step by step you can solve very easily. Yeah, this is example is 9, 8, and 1. Define complete solution of VT. This is the final example we want to solve this chapter. And actually, in this semester, we have learned many things to solve this problem. This is the final things. Okay. We will solve the problem first here then. Okay, first, this is the first thing here. Then the circuit looks like more complicated compared we did before. Then our target is find the complete solution. You know, the VT, the voltage is VT. So step 1, then we have to find out the initial condition. To get an initial condition, the switch is changed at t equal to 0 from the here to there. So we need to draw the simple initial of the circuit like that. It's 10 volt in resistor, and inductor resistor here, and the capacitor. And because in the initial conditions, the source is a constant, therefore in the steady state, the capacitor looks like open and inductor is like the short. So this is short circuit, and this resistor here, the 6 and the 4, and this is open circuit because capacitor is open when there is steady state in the DC constant source. Therefore, the V0 minus is division of voltages 4 and 6. 4 plus a 6 and 6 and source is 10. So there will be 60 volt. Then in this case we have to know the current over here. This is I. So in this case the I 0 minus is V divided by the R is 10 divided by 10 is 1. So we got it, the initial condition over here. Then step 2. We make simplify the circuit. How can you do that? Because the circuit changed over here, then circuit looks like here the Vs and here resistor here and inductor and resistor and capacitor this way here. So this is the V, we know it. Then this is a 4, this is a 6, it's a 1 healthy, and this is a 1/4 farad. And define, then this current is IC, we define here. So based on here, we define this current is I. Then we need to drive the step 3 is drive the differential equation from the simplified circuit. So we can do that here. That is from the here Vs will be the same way. This current is the sum of I and IC. So for this current will be I plus IC. Therefore, I plus IC plus V. Then V is L is 1 dTd plus the 6 resistor, so 6 and I. Then what's IC? IC is C dTdV, so 1/4 dt dV. So actually our target is to get the voltage. So we replace all current and voltage. It's like that. So we using the operator method. Then we can replace the V is Si plus 6I. So from here I is 1/S plus 6 the V. Then also here IC is 1/4 SV. So we insert that value here. We rewrite here is Vs equal to 4. I is 4I plus 4IC plus V. Is the 4 instead of I we use here 1/S plus 6V plus IC is 1/4 SV plus V. So we make more simplify the S plus 6 4 plus here it is 4. It's 4. It's 1S plus 1 V. Therefore, we can make a simplify S plus 6 and S squared plus 6S plus S plus 6 plus 4 V. There will be S plus 6, S squared plus 7S plus 10V is Vs. So we rewrite here. Vs equal to s plus 6 and s squared plus 7s plus 10v. Therefore, s plus 6 vs equal to s squared plus 7s plus 10v. Then we change s is to dt d. Then we replace here. Then dt square d square v plus 7 dt d v plus 10v will be dt d vs plus 6 vs. That is the target, the second order differential equation form here. Then step 4, find the natural response. Based on here, we got the characteristic equation is s squared plus 7s plus 10 equal to 0. Therefore, s is minus 2 or s2 is minus 5. Therefore, v and t will be a1 exponential minus 2t plus a2 exponential minus 5t. Then step 5, find the first order response. Then to get the first order response, we need to find out that the variable is vs here. Then v of t is dtt vs plus 6 vs. Then the vs was the vs, here the vs is like that. The vs is 6 exponential minus 3t, so we use here. Then v of t is minus 18 exponential minus 60 plus 36 exponential minus 60. There will be 18 exponential minus 60. So that is 18 exponential minus 60 here. So let v of t, oh no, this is not v of t, this is actually ft. This is ft, because this is ft. So v of t is a form over here. This is the b. Oh, I'm sorry, this is not 6. Wrong. This is not, because it's a 3. So this is not, this is 3. And 3 and 3. So b is v of t is b exponential minus 3t. Then we need to find out the b. I can do that. You apply these terms to the here. So dt squared b exponential minus 3t plus 7 dt d is b exponential minus 3t plus 10 b exponential minus 3t is 18 exponential minus 3t. Then this is a 9b plus minus 21b plus 10b is 18. Therefore, b is minus 9. Therefore, v of t will be minus 9 exponential minus 3t. We got the first response over here. Then step 6. This is complete. solution. Vt is x and t here. Okay, we write Vt is a1 exponential minus 2t plus a2 exponential minus 5t plus force response. So this is not plus, it's a minus 9 exponential minus 3t. And to get the A1 and A2, we have to use the initial condition. The Vigarde initial condition is here. What is that? V0 is 6 and IO is 1. So V0 is 6 and I0 was 1. So at first we need to know the dt dv. So to get here, we need to derive that variable from this second here, this second. Then what is that? How can we get there? It's very simple. How can we get here? From here, we got the v s is 4i plus 4 4ic and plus and v. Then ic is 4i plus 4ic is c dtd v plus and v. So c is 1 over 4 because c is 1 over 4, so that is 1. So vs equal to 4i plus dtd v plus and v. So therefore dtd v is minus 4i and minus v and my plus and vs. So dtd v0, that means the I0 is 1, so minus 4, and v0 is 6 and minus 6, and vs was 6 exponential minus 3t. So when t is 0, then that value is 6, so there will be plus 6, there will be minus 4. So we got it. The dtd v0 is minus 4. So we eliminate this term here. So we got it. Dtd vt is minus 2a1 minus 5a2 and plus 27. There will be minus 4, and vt equal to 0 will be a1 plus a2 minus 9 is 6. From here we got it, the a1 is 44 over 3 and a2 is 1 over 3. Therefore final vt is 44 over 3 exponential minus 2t plus 1 over 3 exponential minus 5t minus 9 exponential minus 3t, the volt here, when t is other than 0. This is a complete solution of this problem. So when you solve these, the complicated the second order, the circuit, when you need to keep the step 1 and 2 and 3 and 4, 5, 6, and you can easily solve to get the complete response of the circuit. This this is 9.9, the state variable. Actually, this is not only covered by electric engineering electric circuit, but also it will be expanded or describe the systems. In the engineering, there are many description methods to represent the systems, but the state variable is one of the most famous the representation method to describe the system. That is state variable. State variable means the variables associated with the system characteristic. We have to choose some variables to represent the characteristic of the system. So in the case of electric circuit, the capacitor voltage or the inductor current can be a state variable to describe the systems. For example, this is example of the circuit. This is R, and capacitor, and the source here. Then we want to describe the systems. Then we need to, if we define the state variable to represent the system characteristic, it's very useful. So because they are capacitors, so we choose the variable capacitor voltage variables, the V1 and V2. Then V1, V2 is a state variable. Then we can make an equation based on the KCL, KVL, or node voltage equations and mesh equations. So we got it. So for example, so what is this current over here? This current is here is the sum of this current and this current. Then this current is we define this as V1. So this current is here VA minus V1 divided by R1. Then this current is this V2. So the V2 minus V1 divided by R2. So this current is the sum of this current and this current. Then current is a C dt dV1 because of capacitor. So we can write this equation like that. The same way, we can make another equation like this. In this case, we need to make a current over here. So you choose in here, this current here. Then this current is sum of this current and this current. Then this current is, this is the V2 and this is the V1. So this current is R2 V1 minus V2. And this current is, this is the VB. So V2 minus VB divided by R3. And this current is sum of this current over this current. And this current is because of capacitor, so C2 dt dV2. Therefore, C2 dt dV2 is the same with the current of this V1 minus V2 and V2 minus VB over R3. So we can make that. Then the delivery term of that is divided by C1 like that. So we can rewrite this dt dv1 dt can be written as a function of system variable. What is system variable? We choose system variable is v1 and v2. So function of v1 and v2 and source is a va. The same way we can make a dt dv2 dt. The variable derivative of the variable state variable. It's a function of other state variable v1 and v2 and input variable is a vb. Then we can make a matrix like that. So d1 and v1 v2 the derivative of v1 v2 equaled the v1 v2 and these parameter represented by the some matrix here. And this parameter can be represented matrix and this is the input. Then we can rewrite. We define the matrix, the V is state variable V1 and V2. And input U is an input. This system input is two input, VA and VB. Then what's that? State derivative of state is some matrix, A matrix and V plus B matrix and U. This is a general formal description of state variable. This is a very useful form. Maybe dtd replaced by the dot. So we'll display here is v dot is a v plus bu. This is a very famous form to describe the systems. So our logic circuit can be represented in the all things. Next is a root in the complex plane. The characteristic of the natural response of second system is determined by root of the characteristic of equation. So example, this is the representation of second order, the differential equation. The x dt squared d2x and 2 alpha dt dxt and omega 0 square xt is ft. So when you make the characteristic equation, okay, you're using that the 0, then we gather the solution of the root of the characteristic equation as it looks like that. So S is kind of a complex number, so we can represent this complex number in complex plane here. This is a real and this is an imaginary here. Then when overdamped, that means this is the real numbers. Then S1 and S2 is a variable, so a real variable, so there's place over here. Then when you meet a critical damped, that means S1 and go to S2, that means two variables going here and meet here. Then after that, the underdamped, there will be some imaginary variable here. So it's go up here and go here. So in this complex the plane, when this S is placed on this real axis, then we call this as overdamped. And this point, this is a critical point, critical damped, and the solution, the root of that S is placed on this plane. Above, if we start from above the real axis, there are some imaginary values that we call there is a underdamped. Is it go up to the here, and it go out to here. That means alpha is 0. What is that? There is no resistance here. So it is an oscillation. So this is a very useful method to represent the characters of second order differential equations. Especially this root, the S is placed on this is a complex plane, left plane here. That means alpha is negative values. We make this alpha positive values. So exponential minus alpha t here, the alpha is positive, so exponential minus alpha t is negative values. That means it's going up, t is infinity, then variable go to 0. So when this S placed in the left side here, then system is stable because of that. But S placed over here, that means exponential minus alpha t here, alpha is negative values. So minus alpha is positive values. So in this case, t is going up. Then exponential positive t will go up infinity. The system is not bounded. There's a problem. We call that is unstable. So when you want to know if system is stable or not, in the case of the system is second order differential equations, then you need to check the characteristic equation and the root of that. The place the root is left side of the complex vector plane, the system is stable. The root is go out here in right plane, the system is unstable. So this is a very famous form to describe the second order differential equation system. it will be covered not only electric circuit, but also the control theory and other many field. So I recommend you to familiar with this approach to analysis the system is like kind of characteristic equations.